Bismillahirrahmanirrahim. Good afternoon, dear students. I hope you are all well. We are going to continue with the subject joint discrete probability distributions, which we started last time. Okay. One over 6, 1 over 4, and 1 over 8, which is the sum of the first line here. If we have a column here for the totals, then the sum of this will be the value here, right? Okay. And remember, when we get the probability mass function for x at 1, what are we going to add? Remember, we said we add over y. So that means you will add this value plus this value plus this value, which means the sum of this one. Remember last time I told you that the marginal of x, okay, will be what? First column and last column, the last column of the sum, right? And if you want the marginal for y, it will be the first row, this row, because this gives you the values of y, and what? The corresponding probabilities, which will be the last row if we add here a line for the sum. Okay, so now remember, what are the values we need? 1 over 6, 1 over 4, plus 1 over 8. So now if we go to the slide we have here, 1 over 6 plus 1 over 4 plus 1 over 8, that gives what? 13 over 24. And fx at 1, again, if you substitute here for x equals 1, so this will be the sum of this joint at 1y, which is this, right? Now expand this summation, so you take y equals 0, so you get f1 0, okay? And y equals 1, you get 1 1, and then y equals 2, you get 1 2. From the previous table you get these values, which, as I told you a minute ago, this will be what? The last row, the last column in the previous table. Now we write the marginal, this marginal, in the form of a table. So we take the values of x. What are the values of x? 0 and what? 0 and 1. What are the corresponding probabilities? 13 over 24 and what? 11 over 24. If we are right, the sum of these two has to be what? Has to be 1. Okay? So again, to get the marginal of x, you add the joint over y. Okay? And if you have a table, then the marginal will be what? The first column and the last column. Okay. Now we need the marginal for y. By definition from last time, what's the marginal for y? You sum over x the joint probability mass function, and you attach the domain of y. From the table, the values of y were what? 0, 1, and 2. Okay? So now we have, again, you have to get fy at 0, and then fy at 1, and then fy at 2. These three. Fy at 0, fy at 1, fy at 2. So all you need is, in this formula, replace y. Replace this y with what? Here, 0. So you get summation x equals 0 to 1 for the joint x and 0. Now expand the summation. Okay, so if you take x 0, what do you get here? f0 0, which is this one, right? And then take x equals 1, so what do you get? f1 0, which is this. Again, get the values from the table, you will get 1 over 6 and 1 over 8, and she gives you this sum. Okay, you do the same here. If you take x equals what? The second value, 1. So substitute here for x1. You will get this here. fy1 equals the summation x0 to 1 for the joint evaluated at x and 1. And then expand the summation. You have only two values, 0 and 1. So this will be what? F0, 1, and then F1, 1. Here, 0, 1, and 1, 1. You get the corresponding values from the table, add them, you get this. The same with the 2. And then you write them in the form of a table where the first row will be the values of y and the second for the values of the probability mass function of y. Again, the sum of these values have to be what? 1. Okay. And this is another example, example 2. This time we have a formula. In the previous case we have a table. Here we have a formula. So it says let f of xy equals kxy if x is what? 1, 2, 3, and y the same, 1, 2, 3. And it is 0 other y's. Okay. The first part of the question we need k so that this function is really a joint probability mass function. Okay. And then in the second part we need to get the marginal for x, the conditional for y given x, and the conditional, this is the conditional probability mass function, and this is the conditional CDF. Can you see it? This is capital F, but this is what? Little f. So this is the probability mass function of y given x, but this is the CDF, or the cumulative distribution function for y given x. Okay, again, now to get k, again you use what? The properties of the joint probability function. Where one property is that when you add over x and y, you must get what? 1. So now we add from x equals 1 to 3 and y equals 1 to 3. This is the domain you have, okay, or the support of this probability mass function. Replace fxy. What's fxy? Kx times y. K is constant, take it outside, and then you have xy. This sum has to be what? 1, right? Now here these summations, x is constant with respect to this summation. So take this x outside here. So it becomes what? Summation x, summation y equals 1. And then expand each summation. This summation will give you what? 1 plus 2 plus 3. And this one, when you expand it from 1 to 3, 1 plus 2 plus 3. Right? 1 plus 2 plus 3 is 6. And this one is also 6. 6 times 6, 36. So you have 36k equals what? 1. So k is what? 1 over 36. Okay. So we can go back here and replace this k with 1 over 36 to get it explicitly. Now here in B, the first part of B, we need the marginal for x. Again, what's the definition of the marginal of x? It is the summation of the joint probability mass function, and we sum over what? Y, the other variable. Okay? And you attach the domain for x. What's the domain for x from the very beginning? 1, 2, 3. Here it is. So x equals 1, 2, 3. Okay? Now replace f of xy. What's f of xy? It is k times x times y. K now is what? That's what we obtained. 1 over 36. So it will be 1 over 36 summation xy. Right? But x is constant with respect to this summation. So we take it outside. So it becomes x over 36 summation of y. What's summation y? If you expand this summation, it will be 1 plus 2 plus 3, which is 6. So it is 6x divided by 36, which is x over 6. You put it in the formal form. So we say the marginal of x will be x over 6 if x is 1, 2, 3 and 0 other y's. Now remember what's the second question? We need what? The conditional probability mass function of y given x. Okay, what's the definition of this from last time? This conditional probability mass function has to be the joint divided by the marginal of x. The marginal of x is what we got, this one. So that means you want to divide this kxy, and k now is what? 1 over 36 divided by what? X over 6. Okay, here it is. So the conditional for y given x is what? The joint divided by the marginal. The marginal of what? The marginal of x, this variable. Okay? As we said, the joint is what? 1 over 36 xy. What's the marginal? 1 over 6x. Divide this by this, you get what? Y over 6. Okay? So now f of y given x, we write it formally. It will be y over 6 if y is 1, 2, 3, and 0 other y's. Okay? What else the question asks for? It asks for the conditional CDF, cumulative distribution function. Again, what's the definition of the conditional CDF? It is the sum of what? The conditional probability mass function. This is little f and this is capital F. So we sum the conditional probability mass function, okay, for y given x, that as we said, since we have here y, we can use a dummy variable t. Okay, so it is f y given x, t given x, okay, where t is less than or equal y, which means you are going to accumulate, you are going to sum the values of the probability mass, conditional probability mass function, okay, which are in fact probabilities, but conditional probabilities. Okay, can you see this looks like the univariate? It's in fact univariate. The random variable here is y. Remember what do we do in the univariate case? Remember we draw the straight line, okay, and we locate these points on it, 1, 2, 3. So you divide it into intervals, and then you take here for the CDF, you take this sub-intervals. So the first one has always to be what? Y less than 1. The second, between 1 and 2. And you include 1. So it will be y greater than or equal 1 and less than 2. The following 2 and less than 3 and greater than or equal 3. Even without this summation, you can get these values. If y less than 1, does y take any value less than 1? No. So the corresponding probability will be what? 0. This is what we call otherwise. So that means it is 0. Now, y greater than or equal 1 and less than 2. In fact, that means y equals 1, right? Because this is discrete. So that means y equals 1. If y equals 1, what's the corresponding probability? 1 over 6. 1 over 6, right? Okay. If y greater than or equal to and less than 3, what does it mean? It means y is 2. Now if you want y to be less than or equal to, what does it mean? It means 0, 1, and 2, and that's what we mean by add. X goes from 1 to y minus 1. Okay, so that will be this one, right? This is the marginal for x. Okay, so now if we divide this by this, you will get q raised to p y raised to y minus x minus 1, which is this. Again, you attach the domain here. Okay, the main domain here is the domain for y, right? So y goes from what? X plus 1, x plus 2, and so on, and x from 1, 2, 3, and so on. And also we put the values for p and q. What's p? As it is given in the problem, a number between 0 and 1. And what's q? 1 minus p. F of x given 3. Okay, so this is what we want. From the previous part E, just in the previous slide, we have f of x given y equals what? Y minus 1 to negative 1 for this value. You agree? All you need is just replace y with what? With 3. So what do you get? F of x given 3. If you replace y with 3, 3 minus 1 raised to negative 1. 3 minus 1 is 2. 2 to minus 1 is what? Half. And also replace y here with 3. If y is 3, 3 minus 1, 2. So that means x will equal what? 1 and 2 only. 1 and 2. And 0 other y's. Okay? In fact, it's clear that this will be a probability mass function because this is positive, and if you add, if x equals 1, the function is half. If x is 2, the function is half. Half plus half, 1. So it's really a probability mass function. Okay? In G, the last part, we want fy given x for y given 1. So that means x is fixed at what? At 1. Again, from the previous part, from the previous slide, we obtained f of y given x. And it turns out to be what? Q p to y minus x. Sorry, this is not equal. This is given, right? This is conditional. I'm sorry about that. Corrected. Okay. So this is y given x. Okay. So this is what we obtained from the previous slide. All you are going to do is to replace x with what? Replace it with 1. So you get f of y given 1. Okay. So this one is this one. Okay. So f of y given 1 will be what? Q times p raised to y. Now replace x with what? 1. Again, here we don't have, I don't know what's the problem today. Okay, this is 1 also. We have to have 1 here. Okay, so y minus 1, which will give you what? Y minus 2. So now this is the conditional probability mass function of y given 1, which is this. I hope this is clear. I just wanted to give you these 3 examples to be sure that you understand the material we explained last time. So now we finished, okay, and let me just summarize to you. For the discrete case, what did we talk about? We've talked about the joint probability mass function and the marginal probability mass function and the conditional probability mass function. And then we move to the joint cumulative distribution function, CDF. We've talked about the joint CDF, the marginal CDF, and the conditional CDF. And we've talked about how do we calculate probabilities in these joint distributions. We said all you need is to sum over x and y, and you sum over the interval you want. In fact, it's not interval, but I mean the area, we can say. You want the probability on. Okay. Now we are going to generalize these ideas. So now here we say, as a generalization, if we have x1 up to xn be jointly discrete random variables, then what's the joint probability mass function of these x's? We will denote it by fx1, x2 up to xn. Can you see I dropped the index here? before we write the index here, right? But if we write the index here, I'm going to write capital X1, capital X2, so it will look complicated. So that's why I dropped that, but at the same time I will use different letters. If I need to define something else, I will use different letter from F. Now, what's this joint probability mass function? In the discrete case, it's a probability. So it is the probability that x1 equals x1, x2 equals x2, and xn equals xn. And you have to calculate this probability for each n tuple x1 up to xn of capital X1 up to xn, which means for each n combinations of the values for the random variables x1 up to xn within the range of the variables. Okay, that depends on the problem. So this is the joint probability mass function. What's the joint cumulative distribution function? Which we call it capital F. So capital F x1, x2 up to xn will be also probability. But probability that x1 is less than or equal little x1, and the capital X2 or the random variable X2 is less than or equal little x2, and so on up to capital Xn less than or equal xn. Be careful when we use capital letters and little letters. And as you all know, when we try to obtain capital F, we obtain it for the variable between what? Minus infinity to infinity, right? Okay, so we have to do this for each random variable. So that's why we write it xi here, and I is what? What's I here? It could be 1, 2, or what? Or n. So I, 1, 2, up to n. As I said, this is a general definition for the CDF. We are going to write this also when we talk about continuous case. But now here, since we are talking about the discrete case, this type of probability, in order to get it, you are going to use what? Summation, right? So it will be n summations because you have n random variable, and you sum what? You sum the joint probability mass function, this one, right? You sum it over what? You sum it over these regions, right? So that's why we write here S1 less than or equal X1, S2 less than or equal X2, Sn less than or equal Xn, and we use here S1 up to S1. We didn't want to use X1 because if we use it here and here, it will be a little bit confusing. Yeah? Okay, so this is the joint probability mass function and the joint CDF. What else did we talk about? We've talked about the marginal. So if we want the marginal probability mass function of, say, x2, how do we get it? We add over all other variables, right? So f at x2 will be, we sum over all but not x2. Can you see I am adding over what? The first one over x1, this one x3, so I drop the x2. Okay, and then the next one will be x4, x5 up to what? X. So that means to get the marginal for a specific variable, sum over all other variables. What do you sum? You sum the joint PDF, and then you have to attach the domain for this variable. This is x2, and we assume that its domain or its support is what? R2. Okay, what else did we talk about? Okay, can you see in the previous slide, we've talked about the marginal for one variable, x2, right? Sometimes, since you have more than one variables, you may need to get the marginal joint for a subset of variables. For example, here we want the marginal joint probability mass function of what? X2, x4, x5. Okay? So how do we get this marginal joint probability? We add over the other variables. What are the other variables? Here we start with x2, so you add over x1. This is x2, you don't have x3, so you add over x3. You have x4, x5, so you add from x6 up to xn. Here it is. I am going to call it h. I said I'm not going to use f anymore. Okay, so I call it h, x2, x4, x6. So what do we add? We add over x1, over x3, over x6, and then all after this up to xn. What do you add? You add the joint probability mass function. And you have to attach the domain of these variables. So I call it xi belong to ri. I is what? 2, 4, and 5. These indices. Okay. What else did we talk about? The conditional. Remember the conditional probability mass function? But before I talk about this, because maybe you can see that this is a little bit complicated, let me go to the example. Suppose I have x1, x2, x3, x4, and x5. Okay, suppose I have 5 random variables. And I want the conditional probability mass function of x1, x3, x4 given x2, x5. What do we do? Like what we've done in the bivariate case. Take the joint of all of them. Okay, which is what? F x1, x2, x3, x4, x5. Divide by what? Divide by the joint probability function of the variables you are conditioning on, which is what? The joint of x2 and x5. We call it q. q, x2, x5. So can you see it's just an extension for the bivariate case. So now if we go to this general case, here I want to say that we have variables x1 up to xn as usual, but I will divide this into two subsets. Okay, I call the first one xi1, xi2 up to xir, and I call the second xj1, xj2 up to xjs. For example, this subset here is what we call it here, what? x1, x3, x4. And this subset here, which here we have it in the example, what? x2 and x5. So now we say if these two are two subsets of x1, two disjoint, of course, there are no common random variables here, are two disjoint subset of x1 up to xn, then the conditional probability mass function of the first one, the conditional of this given this, will be what? So this is a conditional, will be what? The joint of all of them, this and this. Here it is. F, xi1, xi2, xir, xj1, xj2 up to xjs. The joint of all the variables. And then we divide by what? We divide by the joint probability mass function of the variables you are conditioning on. You are conditioning on this, right? So that means you divide by q, xj1, xj2 up to xjs. And for this ratio to be valid, we have to say provided that this denominator is what? Greater than 0. What's this? As I am saying, this is the joint probability mass function of xj1 up to xjs. And that's why I gave this to make life simple, because this looks a little bit complicated. I hope you understood this now. Again, this lecture is just some examples to make the material we covered last time clear. And be careful about example 3, because this is a good example. It has an idea where the domains of the variables depend on each other. Okay, and this is just an extension for the bivariate case to more than 2. Okay, I hope you understood. If you have any questions, please email me. Okay, and we'll see you next time, inshallah. Or we meet, inshallah, next time. Okay.